My name is Klaus Krohne. I am the Sales Director for Dassault Systemes, Simulia in Asia. I would like to talk to you about the speed of innovation and how you stay competitive in an industry that is currently going through more disruptions than ever before. We have coined the expression ModSim, which in essence means bringing the design and simulation closer together in order to accelerate innovation. And I would like to introduce this ModSim concept to you. We can currently identify 5 megatrends in the transportation and mobility industry. Some are further along than others, but they're all happening at the same time. There is the demand from customers for new experiences in infotainment and cabin design. Then, of course, there is the accelerated trends towards electric, connected, and autonomous vehicles. Then sustainability, regulations, quality control, and cost reductions create immense pressure on engineering departments. Efficiency needs to be improved to enable mass production and mass customization. And then we have mobility as a service, which is challenging the business models of many of our customers, while also requiring different types of vehicles. Simulation touches all of these aspects, but perhaps the biggest pressure is felt by engineering departments comes from the requirements of sustainability, compliance, quality, and cost. It is therefore no surprise that when General Motors, in a press release, shared some of the testing statistics for their 2019 Chevrolet Silverado model. A staggering 7 million miles of testing were required by about 800 test vehicles. Yes, many of those vehicles are production vehicles and therefore less expensive than a prototype. But of course, this also means that they have to wait for the availability of those production vehicles before they can perform the test, at which stage a design change becomes an enormous cost. All in all, they performed almost 500,000 physical tests. And this is just for one model in their product line. Now, I would like to put this in context with a quote from Elon Musk, who said, "Progress in any given technology is simply the number of iterations times the progress between iterations." In fact, he probably tweeted it. I like this quote because it gives us essentially a measure for the innovativeness of an organization. When you want your company to become more innovative, you can, of course, invest in good coffee, beanbags, a ping pong table to improve the motivation and the work environment of your engineers, and that will certainly help. I don't discourage that. But ultimately, you have to ask yourself, how fast can I iterate? So here is an admittedly very simplified flowchart of an innovation process. The key is the loop in the center. The more often you go through it and the more you improve in every iteration, the better your product will be. And this is the reason that GM reports about 500,000 tests for a single model. It becomes also clear that the bottleneck in this loop are those physical tests. Physical tests are expensive, and there is certainly a high pressure to reduce this cost. But in this presentation, I would like to focus on the fact that they're also very time consuming, and therefore they slow down the innovation process. It will not surprise you that from Simulia, the answer to this is, well, just replace all physical tests with simulation. When we suggest this to our customers, almost always the first question is, how accurate, how predictive are those simulations? And this is certainly a valid question. If the simulation gives you different answers from the test, obviously you cannot replace one with the other. However, today this is largely under control through a rigorous deployment process with clear KPIs and KPIs that measure the predictiveness of the simulation. The next concern is maybe best exemplified by this objection that we heard from one executive a couple of years ago. He said, "I can build a prototype faster than you can build a simulation model." Well, if this is true, then by shifting from test to simulation, we are simply replacing one bottleneck with a different bottleneck. And we have very little impact on the speed of our innovation. This also highlights that within the CIE process, the bottleneck is the model build. This is where ModSim comes in. ModSim fixes that. where we have deployed our model build process on the 3D Experience platform, we have measured 2 to 10 times speed up for every single process compared to what was previously deployed. In addition to speeding up the iteration cycle, this also had other positive effects on innovation, as it makes simulation more accessible to more users, to designers, which also addresses another concern. What do all these model build experts do that we have today building our models? What we have seen at companies that have deployed ModSim, that have deployed more efficient modeling processes, is that they have not reduced their workforce, but instead they build more models. It turns out that innovation is more valuable than cost reduction. So to understand this kind of efficiency gain and how it is possible, let us look at a CIE process, a typical CIE process as it is probably deployed in a similar form at your organization. So we go from a design on the left, where we have a CAD database managed by a PLM solution and a fastener database, and they are stored on a network drive. In order to prepare a model, the CAD and the fasteners have to be imported into the preprocessor, which does a automated CAD mid-surfacing, meshing, some connection definition, largely done by scripting, and then to integrate all the model and assemble it. Then we, again, this is stored on a network drive. Then we have the CIE authoring solution, which sets up the simulation. Normally, there are different use cases, maybe for safety, NVH, and durability, which again, the results are stored on a network drive and loaded into a CIE post-processor. In the meantime, you probably have also an orphan mesh that you get from one of your suppliers, which then needs a different process of integrating. And all in all, if we analyze this setup, we say, of course, it depends on the complexity of the model, but like 3 to 4 weeks is for a, let's say, for a vehicle body simulation process is very typical. So what are the problems with this? First of all, there is the silo between the simulation, the CIE, and the designers. Every time we load a CAD or a fastener database into an authoring tool, we create a copy. This becomes increasingly difficult to manage if we have multiple configurations, which then multiply with the number of use cases that we want to test. And then we have the issue of the complexity of the issue of complexity for the fastener definition. This is typically where most of the time is spent in the model build process. So all in all, this makes the entire, these are the root causes for the length and the time that you spend for modeling and creating simulation models. We fix this by bringing all of this to a unified modeling and simulation environment. The user experience on the 3D Experience platform is similar to a social network integrated with a business platform. You have communities, notifications, dashboards, projects, and apps. Most importantly, it provides a single database where all engineering data that is needed throughout the process, a single source of truth that eliminates the need for copies or imports and streamlines the communication between stakeholders. CIE model building productivity is the crucial path for a successful vehicle launch. This gives you faster management, more automated modeling, and a design change synchronization with simulation. So let me show you how this is done in action. One of the most time-consuming tasks is currently the process of the definition of fasteners to CIE connections. Here is where we can make use of the fact that the model build engineer can access the definition of fasteners as they are designed in the CID environment. Next, we go to the meshing. As we have access to a lot of the CID attributes, we can make use of advanced defeaturing mid-surface extraction, and meshing rules and templates that provide an unprecedented level of automation. Next, the fasteners that have been previously defined in the CAD environment can automatically be converted to a CIE connection. And that cut shorts the bulk of the most labor-intensive part of the CIE process. The real magic and innovation happens when you go through this loop again. With efficient communication tools, the simulation expert can communicate the required changes back to the design department, leveraging the issue tracking process that they have in place. After the design engineer makes the suggested change, the whole loop can be rerun with rebuilding the model almost completely automated. This is where we supercharge innovation. But why stop here? Once we have this level of automation, we can bring this to other physics. Here we have our electric drive, noise, and vibration workflow that requires models for electromagnetics, structures, multi-body, and acoustics. If the model build is automated, we can run optimizations and design of experiments across all physics. Which essentially allows us to do trade-off studies that optimize several KPIs, such as power to weight ratio, efficiency, cost, and torque specs, while staying within stress, thermal, and noise limits. So what is ModSim? ModSim is essentially a way to supercharge innovation by iterating faster, which is helped by a high level of automation between the CAD and the CIE process. Thank you for your attention.